Good morning, children. Welcome to online chemistry class of class 11. Today we will start the new chapter, that is unit 5, states of matter. In this states of matter chapter, we have the revised syllabus in which the liquefaction of gases, critical conditions, and the liquid state, these all are deleted. So we will only consider the gaseous state here, not the liquid state, and neither the change of a gas into liquid state. Now, before the beginning of the topic, we have some subunits of this. The first one is intermolecular forces. Next one will be the laws that will govern the behavior of ideal gases under different cases, that is Boyle's law, Charles' law, Gay-Lussac's law, and the application of these laws in various real life situations, combined gas law or ideal gas equation, and the related numericals. So let's start with the intermolecular forces first. And till then, up till periodic table whatsoever we have completed, we have seen that the different elements are having different properties, and we were considering the single particles there, even if in the bond formation of the single atoms, whether it is an electrovalent bond or it is a covalent bond, that is, it is whether formed through loss or gain of electrons through valence shell redistribution, or could be by the sharing of electrons to achieve the nearest noble gas configuration, or even to attain the stability through energy decrease. So howsoever, we were actually considering the individual species as the single one, and thereby we were considering the single particle properties such as size of the atom, ionization enthalpy, the charge density. Charge density stands for the charge divided by atomic or ionic size. This is also known as polarizing power. The molecular shape, polarity, all these we are getting this knowledge from the combined consideration of structure of atom, periodic properties, and chemical bonding. However, this chemical bonding chapter is not included in your midterm syllabus. Most of these observable characteristics of a chemical system with which we are familiar, that will represent the bulk properties of matter. That means it is the properties associated to the aggregate or cluster of atoms. For example, if we consider just the boiling point of a liquid, while boiling a liquid, we will see that a single atom or a single molecule will not boil. It will boil as a bulk phenomena. The liquids are having a property to get spreaded because of their translational motion, and the same thing is for gases also through intermixing or diffusion. But a single particle of gas will not intermix or not diffuse. It will be the entire bulk or cluster of the matter that is showing one particular property. So this properties, the bulk properties, are actually a joint venture of particle attraction or interparticle forces and the thermal energy associated to them. So for this, actually, we need to know first which kind of interparticle force is existing and what is their thermal energy. Then the combined effect of this interparticle forces and thermal energy will finally decide whether the matter will be in solid state or it will be in liquid state or it will be in gaseous state. No matter, its chemical composition could remain same. For example, when we consider water, the most common compound, this water also existing as the solid ice, liquid water and the steam or vapor. But howsoever this is existing, the representation or the chemical entity of water is still remaining as H2O. But the net intermolecular force in water as well as the thermal energy associated to water will, that is the bulk of water or certain given amount of water, will decide whether this H2O will remain in ice form or in liquid water or in gaseous form, that is the water vapor or steam. So, and one more important thing is, it is very important to know what is the physical state of that particular substance or the particular matter. Many of the numericals or many of the chemical processes that will involve the physical state of matter. For example, when you will study the further chapters like chemical equilibrium, we will see that the equilibrium constant, or this is equilibrium parameter, this includes only the matters that are in gaseous state or that are in ionic solution. It will not consider the concentration of pure liquids or solids. Similarly, some of the rates of chemical reactions will also depend largely on the physical state of matter. Therefore, it is very important to understand what is the physical state of matter, which finally depends on two factors. One is the intermolecular force and the second one is its thermal energy. Now, while coming to the intermolecular forces, these are the forces of attraction and repulsion between the interacting particles. It could be atoms or molecules. Now, this will not include the electrostatic force. That means it will not include the ionic bond. The first hand, I want to make this point clear that when A plus and B minus are there in case of ionic bond, or this ionic bond which is not a true bond, which is a cluster of anions and cations, here only electrostatic attraction or Coulombic attraction is present. We are not considering this as intermolecular forces. We will consider only this force that is present between the molecules attached through the covalent bonds. That is, if AB is a covalent molecule and another AB is also a second covalent molecule, which kind of interaction is present in between these two is our prime concern over here. This interparticle attraction could be in the form of attraction, could also be in the form of interparticle force, could be in the form of attraction, could also be in the form of repulsion. Now here we will consider the attractive intermolecular forces, which are known as van der Waals forces. This van der Waals forces are only, as I said earlier, these are only attractive in nature. In this van der Waals forces, we are actually considering the London dispersion force, the dipole-dipole attraction, dipole induced dipole attraction, and hydrogen bond. So for this, let's first start with dipole-dipole attraction. In this dipole-dipole attraction, it is true that the molecule must be a polar one. That means it must have a permanent dipole. What is that dipole? It is a vector quantity that is directed towards more electronegative atom. Of course, when this molecule is being formed, HCl, there is a large electronegativity difference between hydrogen and chlorine. Thereby, this shared pair is always distorted towards more electronegative species, creating a slight negative charge over here and a slight positive charge over here. The slight negative charge over here, this del plus or del minus, these are numerically equal, means their values are same, only their type of charges would be different, and these values are much less than 1.6 into 10 to the power minus 19 coulomb, which is equal to plus minus 1 unit of charge. This is much less than 1 unit of charge. So in fact, when we have such a polar molecule, the product of charge and the bond length, that is the shortest distance between the nuclei of the covalently linked particles, this will determine the dipole moment. Here first the bond moment and the vector sum will tell the dipole moment. Anyway, in order to be a molecule polar, it must have a non-zero permanent dipole moment. So if we consider this HCl molecule, there are two HCl molecules with del plus at the hydrogen and del minus at Cl. So it's obvious that this Cl slightly negative and this hydrogen slightly positive will have a slight interaction, which is called dipole-dipole interaction. This dipole-dipole interaction in stationary polar molecule, that is the static polar molecule, is proportional to 1 by r cube, that is inversely proportional to the cube of the distance between two molecules, and when these are rotating, it is proportional to 1 by r to the power 6, where r is the distance between the polar molecules. Howsoever, this dipole-dipole interaction, but it is much less in magnitude in comparison to any covalent bond. Now let's consider the dipole-induced dipole forces. Here it is the interaction between one will be polar and the second one will be non-polar. So the polar one will have a permanent dipole, but the non-polar will not have a permanent dipole. In case we consider the permanent dipole or polar molecule AB, which is having a slight positive and slight negative one over here. Another is hydrogen, which is uniformly distributed. The electron pair is uniformly distributed between these two hydrogen. But what will happen if this hydrogen is close to the Cl, that is the facing the slightly negative one? It's obvious that the electron pair in hydrogen, which was uniformly distributed over here, will be slightly repelled by this negative charge, and thereby creating a slight positive over here and a slight negative over here, because this electron pair, which was uniformly distributed, will now shift towards right side away from this side. Thereby there will be slight less electron density and a slight more electron density, creating a slight positive and slight negative charges. So the induction of polarity to a non-polar species by the presence of a permanently polar molecule is called dipole-induced dipole interaction. Next one is hydrogen bond. Now this hydrogen bond is nothing but it is a special case of dipole-dipole interaction in which this covalent molecule is attached to a electronegative atom of small size. The atom should be highly electronegative and small size also. So in this, only 3 atoms do qualify with that: nitrogen, oxygen and fluorine. This nitrogen, oxygen and fluorine, when these are covalently bonded to hydrogen, that means the compound is either having nitrogen hydrogen bond or oxygen hydrogen bond or nitrogen fluorine bond. In such cases, suppose we have this HF molecule, the slight positive and slight negative. This is also slight positive, slight negative. An interactive force attracting between this positive and negative is called hydrogen bond, or to be more specific, intermolecular hydrogen bond. This intermolecular hydrogen bond is much larger in magnitude than the so-called dipole-dipole interaction. Thereby, we will call this as some special category of dipole-dipole interaction, or this is the hydrogen bond. Though it seems to be very simple, but this hydrogen bond has a large impact in various physical and chemical properties and the stability of various molecules. And this hydrogen bond is the strongest van der Waals attraction. Though chlorine is strongly electronegative, but due to larger size of Cl, it will not come to the inclusion of the formation of hydrogen bond. Next, the last one, what we'll come to, dispersion force or London dispersion force. What does it tell? That atoms and non-polar molecules. Now, first thing I want to tell here, in dispersion force or London dispersion force, both the covalent molecule will be non-polar. That is, it is the interaction between a non-polar and a non-polar molecule. Now here the atoms and non-polar molecules are electrically symmetrical. That means they have the uniform distribution of electron pair among them. So they have no dipole moment because their electronic charge cloud is symmetrically distributed. Here, if it is hydrogen, hydrogen, it is symmetrically distributed in between this. Or in case of Cl, Cl also, it is symmetrically distributed. There is no plus or minus existing over here. But dipole is developed momentarily even in such atoms or molecules. Now, how could we explain this when this is a symmetrical distribution of A or B, and in this symmetrical distribution, what happens that during this revolution, suddenly the charge cloud becomes unsymmetric. Charge cloud goes little more on one side, and this results in the development of instantaneous dipole or a very temporary dipole on one atom for a short time. This instantaneous or transient, that means a short span dipole, is affecting the charge distribution of atom B, and thereby it creates a instantaneous dipole over here, the slight positive over here, and the electron density is large at that side. So this electron density of this will cause a slight attraction or repulsion of the electron and attraction of the positive charges, creating the moving away the electrons from the side and creating a slight positive charge over here. So this instant dipole creates certain interaction that is called London dispersion force. The most important evidence of this London dispersion force is the inert gases or even hydrogen or Cl2 that can be liquefied. So even if these are the non-polar species, they can be liquefied, means we are able to increase their intermolecular attraction. Now in case we consider there is no interaction existing, so if zero interaction would be existing and even we can multiply 0, then 0 will still remain as 0. So since it is increasing, we can multiply the intermolecular forces or we can increase the intermolecular forces, which shows the presence of even very small but a finite intermolecular attraction, and that is called London dispersion force existing in non-polar molecules. That's all today. Next class we will discuss about the thermal energy and the relative intermolecular forces, and then we will start the various gas laws.